Okay, hello everybody. I hope all of you are safe and sound. I'm going to start our new session. I have a brief. I'm going to have a brief review of what we have taught in our previous session. As you may know, in our previous session, we talked about a special case when our functional is function of more than one dependent variable, or in other words, we have n unknown functions q1 to qn, and our functional is represented in the following form. I is a function of I is equal to integral from t1 to t2 of f of q1 to qn, q dot 1 to q dot n, and t d of t. Let's say that q dot I represents derivative of qi with respect to t, or in another word we can say q dot 1 is dq1 over dt, q dot 2 is dq2 over dt, and so on. We are going to determine a set of unknown function q1 to qn, which are certainly twice differentiable. To have a second order differential equation, this function must be second differentiable, and with these functions we are going to externalize the amount of functional I. Okay, we are going to use the same method as we have used in our previous sessions. Let's say that q1 to qn are the solution to the functional problem, or in other words, let's assume that by q1 to qn are externalizing our functional I. And now we are going to use the following single parameter family of admissible functions. Let's say that q tilde 1 is q1 plus epsilon eta 1. Q tilde 2 is q2 plus epsilon eta 2, and so on. By using this definition, we can easily say that I tilde, as we will define in this slide, in this equation, I tilde is function of epsilon, and by assuming that q1 to qn is the solution of our functional problem, we can easily say that I tilde of epsilon is a single parameter function and only function of epsilon, and we can say that this function I tilde has its external value at epsilon is 0. Or in another word, we can say that derivative of I tilde with respect to epsilon at epsilon is 0 is equals to 0. By using this derivation, we can easily show that derivative of I tilde with respect to epsilon can be obtained by the chain of rules, or in other words, we can say that the derivative of I tilde with respect to epsilon is equals to partial derivative of f with respect to q tilde multiplied by derivative of q tilde with respect to epsilon, as we can see here. Derivative of q tilde with respect to epsilon is equals to eta 1, and we can do the same for another n function. So we can say that derivative of f with respect to q1 multiplied by eta 1, derivative of f with respect to q tilde 2 multiplied by eta 2, and we can write this until function q tilde n, and we can do the same for q tilde dot 1, q tilde dot 2, and q tilde dot n. From the previous slide, we can easily say that q tilde dot 1 is equals to q dot 1 plus epsilon eta dot 1, q tilde dot 2 is equals to q dot 2 plus epsilon eta dot 2, and so on. So we can easily say that partial derivative of q tilde partial derivative of q tilde dot I with respect to epsilon is equals to eta dot I. So we can say that partial derivative of f with respect to q tilde dot 1 multiplied by eta dot 1, and so on. Integration of this equation with respect to t from t1 to t2 must be equals to 0 at epsilon is 0. Now, by setting epsilon is 0 in the above equation, in this equation, we can say that at epsilon 0, q tilde is equals to q, or in another word, q tilde I is equals to equal to qi. So we can say that partial derivative of f with respect to q tilde at epsilon 0 is equals to partial derivative of f with respect to q1, and or in other words, we can drop the tilde from the above equation at epsilon is 0. By using this and by doing integration by parts, as we have did before, we can easily show that, for example, for eta 1, integration from t1 to t2 of partial derivative of f with respect to q1 minus d over dt of partial derivative of f with respect to q dot 1 multiplied by eta 1 dt is 0. We know that eta 1 is a set of admissible functions, and using fundamental lemma, we can easily show that, or we can conclude that the coefficient of eta 1 is 0, or in another word, partial derivative of f with respect to q1 minus d over dt of partial derivative of f with respect to q dot 1 is 0. This is our main equation, or our first main equations. We have n unknowns in these problems. We must determine n functions q1 to qn. So we need n equations. We can rewrite the same equation for Q2, Q3, and so on. Or in other words, we can say that partial derivative of f with respect to Qi minus d over dt of partial derivative of f with respect to Q dot I is 0 for I is from 1 to 10 n. Okay, let's continue. As you can see here, now we have n ordinary differential equations. By solving these ordinary differential equations and using boundary conditions, we can find our n unknowns q1 to qn. Let me explain something else. Let me say that all of these equations are second order equations. So for each equations we need two boundary conditions, or in other words, for each qi we need two boundary conditions, and by using these boundary conditions we can solve equation 231. Okay, let's explain the above equations by solving an example. In these examples, we are going to use Hamilton principle in order to find equations of motion of n rigid body motion problem. We will speak about Hamilton principle in details in our next chapter. But here we only introduce this principle, and we only use it in order to find equations of motion. Hamilton principle can be said that for a system, for any arbitrary system, if T is kinetic energy of the system and V is the potential energy of the system, in this system I, which is known as Hamiltonian, is integration from T1 to T2 of T minus V dt has a minimum value for any combinations of our degrees of freedom or our xi. And by using this principle, we can find equations of motions, or in other words, we can find the variation of xi with respect to t, with respect to our independent variable t in any arbitrary time. Okay, now let's speak about our problem. Let's say that we have let's consider that we have two identical masses m and m. Let's say first mass is the left mass is moving from the origin x1, and the second mass is moving from the origin x2. We can easily say that this is a 2 degrees of freedom system. If we know the value of x1 and x2, we can determine the position of the system in any time. So this system is a 2 degrees of freedom system, or in other words 2DOF system. Let's assume that there is no friction between blocks and the ground, so we neglect the friction force. And let's say that the left mass is connected to the ground by the spring K1. The left mass and the right mass are connected to each other with the spring K2, and the right mass is connected to the ground with the spring K1. This is our problem, and let's say that at x1 is 0 and x2 is 0, the system is on its equilibrium point, or in other words, the springs are unstretched at x1 is 0 and x2 is 0. Okay, I want to use Hamilton principle to find equations of motion. In order to use Hamilton principle, as we introduced in this slide, we need to calculate two important terms. We need to calculate T, kinetic energy, and V, potential energy. Okay, let's calculate the value of T. T is the kinetic energy. We can easily say that it's equals to 1/2 of m multiplied by x, the velocity of mass 1 by 2, which is equals to x dot 1, plus 1/2 of m multiplied by the velocity of mass 2 by 2, which is equals to x dot 2. So this is the value of the kinetic energy. Now let's calculate the value of the potential energy. It must be somehow difficult, but we can explain it easily. Let's assume that the first mass is moving to the right, the first mass is moving to the right for x1, and the second mass is moving to the right by the value of x2. So the displacement of the first mass is x1. Let me show you here. Let's say the displacement of the first mass is a positive value x1, and the displacement of the second mass is the positive value x2. Okay, if x1 is a positive number, we can say that the left spring, this spring, is compressed, and the potential energy of this spring is equals to 1/2 of K1 multiplied by length change, which is equals to x1 multiplied by x1 by 2. This is x1 by 2. This is the potential energy of the left spring. The potential energy of the right spring, this spring, can be calculated by the same way. If the displacement of mass m is x2 and x2 is has a positive value, we can say that the spring K1 is stretched by the value of x2, and the potential energy of this spring is calculated by this formula, 1/2 of K1 multiplied by x2 by 2. Now let's speak about the middle spring, which is somehow tricky. Let's say that if x1 and x2 is equal to each other, we can easily say that there is no length change in the middle spring. If x1 is greater than x2, we can say that the middle spring is stretched for the value of x1 minus x2. Or if x2 is greater than x1, we can say that the middle spring is compressed by the value of x2 minus x1. There is no difference if we use x1 minus x2 or x2 minus x1. All of them reached to the I'm sorry, all of them reach to the same value of the potential energy. So we can easily say that the potential energy of the middle spring is equals to 1/2 of K2 multiplied by the length change of the middle spring by 2. Okay, the length change of the middle spring can be calculated as absolute of x2 minus x1. Okay, if I power this value by 2, we can say that x2 minus x1 by 2 is equal to x1 minus x2 by 2. So there is no difference if I use x1 minus x2 by 2 in this term or x2 minus x1 by 2 in this term. Okay, in this equation you can easily see that the potential energy of the middle spring can be calculated by this formula. Now we have the value of T and the value of V. The problem is now very easy. We can only need to substitute T and V in the Hamilton principle, as we can see here. Now our function f is this function. This is our function f, and we can use the Hamilton principle to find our two unknowns x1 and x2. Because we have 2 degrees of freedom, we have 2 unknowns, and we must obtain 2 differential equations. First differential equations can be obtained for x1, so we can say that partial derivative of f with respect to x1, which can be calculated by this term, minus d over dt of partial derivative of f with respect to x dot 1, which can be calculated using this term, is 0. And partial derivative of f with respect to x2 minus d over dt of partial derivative of f with respect to x dot 2 is 0. And by doing derivation, you can do it by yourself. It's very easy and straightforward. By using derivations, we can easily obtain the equations of motion, as you can see here, and rearranging the above equation, we can reach to the final ordinary differential equations, we can easily see that we have two ODEs of order 2, and we need two initial conditions for each of xi's to find the set of equations f. If we know the value of x1 and x dot 1 at time 0, and if we know the value of x2 and x dot 2 at time 0, we can easily solve the above equation. You may be familiar with in your previous lectures. You may be familiar with the procedure of the solution of this equation in your previous lectures. Okay, it's enough for now. I'm going to explain. I'm going to I'm going to continue our course in our next video.